Hi, everybody. Thank you for joining me today. I'm really happy you guys are here. My name is Greg Holden. I'm a STEM ambassador at Pasadena City College. Today, we have a workshop talking all about floating about with buoyancy. What this workshop is going to be about is talking all about how and why objects float. So let's get into it. Today, what we're going to be looking at is a quick physics foundation. We're going to be talking about the actual physics behind how and why things float. And then we're going to talk about what is buoyancy itself. Then we're going to go into a quick buoyancy experiment. It's going to be a cool little experiment you guys can do at home. And then we're going to do a buoyancy simulator. There's a really cool online resource that's going to let you guys play around with buoyancy, and I have some questions for you guys to answer about that. Then we're going to talk a little bit about what is displacement, and I'll have another video you guys that'll be linked to that you guys can watch. That's super helpful with that concept. And then finally, I have a fun little tin foil boat challenge for you guys to do at home. Now, a quick little fun fact for some of you guys that may not have known this is manatees actually regulate their buoyancy by storing and releasing their farts. So if you ever see a manatee floating around in an aquarium and all of a sudden you see a bunch of bubbles leaving him and he goes down, might want to think about what's actually going on there. All right, so moving forward. So like I said, my name is Greg Holden. So what am I interested in studying / majoring in? My primary focus is mechanical engineering. I really enjoy studying how things work and why they work in that way. I love to take things apart and just figure out how can I improve the way it's designed, or what are the good components of its design. So what school would I like to attend once I finish in order to finish my degree? I think my top school right now is Cal Poly San Luis Obispo. They have an amazing mechanical engineering program and a really beautiful campus. It's definitely my dream school to go to. I think outside of that, I would go to Cal State Long Beach. They also have an awesome program there, and it's relatively close to where I live. So what is my favorite thing about STEM? So STEM for me, I think the thing I enjoy about it most is just the really broad amount of skills you can learn and acquire from it. For those of you who don't know, STEM stands for science, technology, engineering, and math. And each one of those different categories has such a huge range of different like skills you can actually learn, different specialties that you can gain in each of those different concepts. And I love exploring the different intricacies of each one. So now, how have you guys been spending your quarantine? I'd love to hear about how you guys are spending your quarantine, how everyone's doing, what you guys have been up to. You guys can shoot a comment down below in the comment box. Personally, I've been spending a lot more time with family because I'm not actually in my classes. I can do my classes from home. So that's kind of nice. And plus, since I'm home a little bit more often, I have a couple of projects around the house that I've been helping my dad work on, such as working on some stuff in our garage, and we've been working on a fence project we have in our backyard. So let's talk about physics. So we're going to do physics in a flash. It's okay if you guys are never done physics before. We're going to make this super easy, super simple. We're just going to talk about a couple concepts and then introduce a little bit of math involved, and then we'll show you guys how to apply those concepts. So what is physics and why is it important? So the definition of physics is the branch of science concerned with the nature and properties of matter and energy. That's really important, that it's the nature and properties of matter and energy. It really, physics focuses on describing how things work in the world. Why does a car move? Why does a plane fly, right? Why are we able to walk with shoes? Why don't our feet just slip and slide on the floor? Why do we fall back down to earth when we jump up in the air? It really just focuses on explaining the physical world as we see it and how we interact with it. So some important concepts. We're gonna have a few really important concepts that we're gonna talk about today that are gonna go through, and you'll see reoccur as we go through the concepts later on. So a big one is force, right? What is force? So in physics, force is the push or pull on an object with mass that causes it to change its velocity or its speed. So now velocity and speed are the same thing, more or less. Now force, the way it works is just like if you were to push down on a chair when you stand up in order to get out of the chair, right? You put a little bit of force down on the chair and it helps you move up, right? You all of a sudden go from being in a steady stopped position with no speed, and you push down and now you're moving upwards with a certain speed. That is kind of how force works, right? If you throw a ball, the ball goes from not moving at all in your hand and you throw it, and now that ball is moving at a certain speed. Just like we see here with these basketball players. Force also, right, you can work at it like this, where one person pulls, or you have two people pulling on a rope. If one person pulls more than the other person, such as this guy in the red shirt looks like he's pulling a little bit harder than the guy in the green shirt, then we can assume that this guy in the green shirt is going to get pulled towards the guy in the red shirt. So therefore, both of these guys are going from no speed at all to both moving to the right. So that's really important to kind of grasp, is this idea of force and how it works. So now a big concept also is the concept of mass versus weight. Now this can be kind of confusing, so I'm going to go a little bit slower here and really kind of go through this thoroughly for you guys. So let's talk about mass. So the mass of an object is a measure of the amount of matter it contains. So everything in the world, right, every little object, anything that you can feel, touch, has mass. It's just the sheer amount of stuff in that object. Now here on Earth, that object that has a certain mass also has a weight to it. These are two separate concepts. Now the weight of an object is a measure of the force exerted on the object by gravity. So here on Earth, we have a very specific gravity that's special to Earth, right? If you were to go on, say, the moon has a gravity very specific to it. And so you'll find that although you have two objects that are the exact same mass, like we have here, right? We see our astronaut here who has mass of 100 kilograms, and we see our astronaut over here on the moon who has also a mass of 100 kilograms. These guys weigh very different amounts because here on the Earth, the gravity is much stronger than the gravity here on the moon. So although these astronauts have the same amount of matter inside of them, they will weigh different amounts depending on the amount of gravity pulling on them. Yeah, so that's super important to kind of grasp. So really take your time here and kind of get this concept down, because this will be really important later on. You can have two objects that are exact same mass, but can exert, but will be weighed different amounts depending on the amount of gravity pulling on them. So our next concept here is density. Density is also super important. This is going to be kind of the keystone concept of our physics equations later on. Now density is, so the density of a substance is its mass per unit volume. And more simply, it's really how much matter is compacted into a specific space, right? So say I have a baseball. That baseball is going to have a very specific density because there's a certain amount of matter inside of that space that is the size of the baseball. If I were to take that same amount of matter and increase it to the size of, say, a beach ball, then now that beach ball will be less dense than what it was in the baseball. And you can kind of see that here, right? So we talk about low density, medium density, high density. So we have a cork and a rock, right? And for argument's sake, let's say that these two objects are the exact same size. This rock here is going to have a much higher density. There's going to be much more stuff in the amount of space that makes that rock than this cork over here. So this rock is going to have a higher density than this lower density cork. And that's going to be important because we see now that this cork is floating and this rock is not. So we're starting to think that, oh, maybe density has something or has a role to play when it comes to buoyancy. And when we talk about physics, this is the equation that we use to actually calculate mass, density, and volume. So we have the volume of an object, which can be defined as mass over density. We have the density of an object, which can be defined as the mass over the volume. And then we have mass, which is equal to density times the volume. So if you haven't yet got to this or got to physics yet in school, you will eventually start to learn about, when you do get there, you'll learn about this mass, density, volume triangle. And this is a really great way to help you calculate each one of these different properties of an object. Our next concept is buoyancy. So this is our big concept, right? Buoyancy. What is it? How does it work? So in physics, buoyancy is a force of an object, is a force on an object caused by a fluid that object is in, making that object either rise or move opposite from gravity. So we see here that we have our little piggy and he's attached to a bunch of balloons. So we know that balloons will float in air, right? Because they're filled with another gas that is it's lower density than air, all right? Typically helium. So now if all these balloons that make this, that float in air, if we attach enough of them to this pig, then it will actually lift the pig up in the air, right? And now this entire system right here, both the pigs and the balloons, are going to float. So this force causing the pig to go from just sitting on the ground normally to all of a sudden moving at a speed upward is called our buoyant force. And this force is now stronger than gravity, so now both of these objects are going to move up. So we can think about this just as we did with the two men pulling on the rope. You have buoyant force that's going to be pulling much harder than gravity, and eventually both of them is going to start moving in the direction of the buoyant force is pulling. So right here is actually a picture. This is going to be super helpful to help explain this a little bit better. Is we have the this funny looking P fluid and this funny looking P object. These are actually, this is the symbol for density. This is pronounced rho, R-H-O. And when we talk about density, right, we have our gravity here, our buoyant force here, right? Our buoyant force is acting up on the object, right? Opposite to that of gravity. And our gravity is acting down just like it normally would on Earth. We have our mass of our object and then these two densities. And we're going to learn about the relation between all of these different factors here and how that pertains to finding out if something can float or not. So what is buoyancy, right? So this concept is the ability or tendency to float in water, right? Air or some other fluid usually works as a force that opposes the force of gravity. So this is really cool because you can visually see buoyancy working, right? You've noticed this when you put on like a little pool floaty and you go into the pool, you'll notice that you'll float, right? Versus if you don't have that on, humans tend to sink in water. So now what we can see is we have on the right side all of these different objects, and each of these different objects will have different densities to them. And over here on the left, we'll have different liquids, different fluids, and each of these different fluids also have a different density to them. And what's really neat, which we can observe, is as these densities change between these different objects and these different fluids, some objects will float on some fluids but sink in others. So example, we have this cherry tomato right here sitting inside dish soap, and it's on top of the milk, which means that it looks like cherry tomatoes will float in milk, syrup, corn syrup, and honey. However, cherry tomatoes do not float in water, vegetable oil, rubbing alcohol, or lamp oil. So this can be really cool because you guys can try this at home, and I definitely recommend you guys do that. We have a link down below in the description box that actually links to the video of this exact experiment that you guys can try out for yourself. Now, don't worry if you don't have all of these items that the gentleman had in this video. You can use any collection of these items and these fluids to actually do this experiment if you don't have all of them. So definitely go and check that out. It's super fun to try and see at home. So now let's start talking a little bit about the conceptual physics of buoyancy. So buoyancy has three main types, right? We have positive buoyancy, neutral buoyancy, and negative buoyancy. Now, when we talk about buoyancy, right, it's the force acting upwards. We're going to call that the buoyant force, right? That's this letter B right here in each of these little diagrams. And then the force acting downwards, the opposite of buoyant force, is going to be gravity. And that's going to be this letter G here. Now, when we talk about positive buoyancy, this is a good thing, right? Positive buoyancy means you have, you are going to float in water. So whatever you put in the water, right, we're talking like a ping pong ball in a glass of water, right? The ping pong ball is always going to float on top. And that's described right here by this yellow block. See that this buoyant force arrow is much larger than this gravity. And so therefore, all of this system is going to move up. It's going to get a velocity upward, and it's going to start to float up here. Now, this also means that the object itself is less dense than the fluid. That will give you a positive buoyancy. This is really important concept, right? The object that has whether it's the fluid that has more density or the object that have more density, depending on that relationship, is whether or not the object is going to float or sink. So if I have an object with less density than my fluid, my object will float in my fluid. If we now go down to neutral buoyancy, notice that these arrows are the same size now. We have an object that has the same density as that fluid. So we have an object and a fluid, exact same density. The object will not be able to float or sink in the fluid. It'll just move to wherever you let go, and then it'll just stay put. It's kind of a cool phenomenon to see this happen. And finally, we also have negative buoyancy. The negative buoyancy is when your object is more dense than your fluid, and therefore it sinks. This would be like a metal ball inside of a cup of water, right? You're going to drop the metal ball, it'll go straight to the bottom. There's no way it's going to float on that. Yeah, so these three concepts are really important to remember, especially the relationships with their densities. So you have positive buoyancy, object is less dense than the fluid. Neutral buoyancy, same density for both object and fluid. and negative buoyancy, the object is more dense than your fluid. So now let's talk about the math relating to these concepts. Now, don't get too worried if you haven't gotten this far in math yet. I'm going to go through this stuff real slowly, and this is more just so you guys can kind of see the relationship of density and how big of a factor it plays into the buoyant force. So we see here we have our force for buoyancy, right? Our buoyant force equation. So force of buoyancy is equal to the density of our fluid, our rho F. This is how you pronounce this guy right here, right? Rho F. Density of our fluid times the force of our gravity times the volume of our object. And now we can also see down here that density, which is our rho S, is equal to the mass of the solid divided by the volume of our solid, right? And that's what we got from that triangle. Now what we can see here is that this equation, rho S equals m divided by v, can be translated into, using algebra, can be translated into v equals m divided by rho S. Now this is really important because we can take this equation right here, and because we know what v equals, we can substitute this m divided by rho S into our equation up here for buoyant force. So now when we combine these two, we see that our buoyant force equals m times g times the rho of our fluid divided by the rho of our solid, which is the density of the fluid divided by the density of the solid. So what that means is that no matter how heavy the object is, we can have an object that weighs, or that is 1,000 kilograms or 10,000 kilograms. As long as the density of our fluid is greater than the density of our object, then the object is going to float, right? We're going to have a positive buoyancy on the object, and the object is going to float up. And it doesn't matter how big it is. This means you can float an object that's as heavy as you want, so long as the density of that object is less than the fluid you are trying to float it on. So now let's actually try this. This is a really fun, we're going to play with something called the Phet buoyancy simulation. This is an awesome little website you can go to that lets you actually mess around with these different buoyancy concepts. So down in the description box, you'll see a link to something that's called the Phet buoyancy simulation. Go ahead and click on that link, and then I will walk you through kind of how to work it, and then I'll have some questions for you guys on what that looks like. Okay, so here's the Phet buoyancy simulator. So now what I'm going to do is I'm going to walk through a couple of controls that this simulator has, and then I'm going to show you guys some questions. And I want you guys to go through and try to answer those questions. So first, let's talk about some controls, right? So we see we have a couple blocks here, and you can click and drag on these blocks and move them around. We can throw them in the water, and we see that the wood floats as we would expect, and the brick would sink just as we would expect it to. We also have some scales here, but we won't necessarily be using those today. So now what's important is we see that we have multiple option boxes around here, right? We have same mass, same volume, same densities. So if we start with the same mass, and we see that we also have show forces over here. Let's turn on gravity and buoyancy, and let's also turn on the force values box. Now these three boxes are now on, and we get to see that we have 49 newtons of blue, which is our gravity force. And if we pick up this wood block and drop it in the water, we see that once the block starts to stable out and floats, we see that we're going to get 49 newtons of buoyancy force. And this is showing us what is a positive buoyancy, right? Because if we were to pull this block under the water and let go, it ends up floating again. Now, if we do this with the brick, we drop the brick in the water, we see that we're only going to get 24.5 newtons of buoyancy force. Now, this buoyancy force is being driven by that density relation between the water and the brick. So there's no way for us to increase that buoyancy force. So no matter what we do with this brick, it's always going to sink in water. So now let's talk a little bit about some of the questions I have for you guys. So let me open up our slideshow here. So here's some of the questions I have. So question one, why does the wood block float and not the brick? So take a second, maybe pause the video for 5-10 seconds. Think about what's going on there. Remember back to some of the concepts we had, and then answer that for yourself. Okay, so question one, right? Why does the wood block float, not the brick? It's really coming down to the density, right? The wood is less dense than the water, and the brick is more dense than the water. So that wood block has positive buoyancy. The brick has a negative buoyancy to it. So obviously the wood block's going to float and the brick is going to sink. just as we would expect in real life, right? But now you guys understand kind of how that works, right? The wood has less matter in this area or in the volume that it has versus the brick. The brick has much more matter in it versus the volume it has. And this is why one floats and one sinks. So question 2, will the wood block with the larger mass sink? So if we go back to our buoyancy simulator, I want to show you guys another cool feature about this simulator. So I'm going to reset, there's a reset all button here that you can reset everything. And now what we do is you go up here and you see we're in intro, click on this buoyancy playground tab. Now in this buoyancy playground tab, you see we have many, many more options. You can completely customize your own kind of blocks, whether it's wood, styrofoam, ice, brick, or aluminum. You can also make a completely custom block with your own custom density. But for this, for these questions, you're going to use these preset blocks. Also, we have our forces, so we can turn on gravity, buoyancy, and our force values. And then down here, we also have our fluid density. So now we can change from water, which is our density here, and we can make it into honey. We can turn it into gasoline. We can turn it into air. You can make it super dense, super thick. But let's leave it as water for right now. And then you can also add a second block. So over here, you can click on 2 blocks, and now we have 2 blocks to choose from. So once you have your simulation set up like this, let's look at question 2 that we just had. We go back to our PowerPoint here. Question 2, will the wood block with the larger mass sink? So what I mean by that is, we go back to our buoyancy simulator, notice how we have a mass here, which is 2 kilograms, and a mass over here, which is 3.2 kilograms. So now before we put either of these blocks into the water, do we think that this wood block is gonna sink now that it has a much larger mass? And even up here, we can see that block B, we can change this mass to be much larger. So we can turn this mass all the way up to 8 kilograms. Now this block is huge, right? The biggest we can make it. And this block over here, we can make this guy really small, right? Let's make him 1 kilogram. Now, if I put both of these in the water, do you guys think one of these, this larger block, is gonna sink versus a smaller block? So let's find out. So if I drop the small block in, awesome, it floats, and we see that we have the 9.8 newtons. We'll eventually balance out with the 9.8 newtons over there. Now, if we put this huge block in here and we drop it in, oh, it will float. So remember when we talked about density before, you can have an object that's 1 kilogram or 10,000 kilograms. It doesn't matter the size of the object, the mass of the object. It really matters what the density of that object is in relation to the density of the fluid it's sitting in. So notice how we didn't change the density of our blocks, right? Both of them are still wood. They're the same density. However, you just have a much larger space that this B block is versus this A block. So it doesn't matter how big they are. It really just matters that the densities are the same. So both the densities right here are 0.4 kilograms per liter. Those are still less than water, which is 1 kilogram per liter, meaning density of our solid is less than density of our fluid, positive buoyancy, both objects will float. We can drag this block under the water, let it go, and it will still float. Okay, so now on to question 3. So let's look what question 3 has. So what does the density of the fluid need to be in order for the wood block to have a neutral buoyancy? So go ahead and go to your simulators and see if you guys can answer this one on your own. Pause the video here for however long it feels it takes you to answer. And then once you play again, I will show you guys the answer. So now let's look at how to answer this, right? So what does the density of the fluid need to be to make the wood block float? So I'm gonna go ahead and reset everything here because we're just gonna have one simple block. I'm gonna turn on our gravity, our buoyancy, and our force values so we can see all that. And I'm gonna throw this guy in there. So now to mess with our fluid density, remember that was down here at the bottom. So I can make this very dense, I can make it not dense at all. And we see that as I change this, the block either floats or it'll sink. And so remember, neutral buoyancy is we want the block to not float or sink. We want it to be able to move wherever it wants in the fluid and not move at all. Once we let it go, it will stay there. And so if you guys remember, the relation for neutral buoyancy is we need the densities to be the exact same. So now we can change the density of our fluid, but we don't want to change the density of our wood block, right? Because if we change the density, then it will no longer be wood. It will represent maybe ice or brick or even aluminum. So what we can see here is that we have a 0.40 kilogram per liter density for our wood, and a water floats right around 1 kilogram per liter. So what we want to do is make these densities equal. So we have
0.40. We hit enter. And now we see that our buoyant force and our gravity force are still the same. However, wherever we move this block is now neutrally buoyant. It is completely submerged and it will not sink nor float. I can move it down here and notice the block won't move up or down. I can move it over here, it won't move up or down. And that's really cool because these are really interesting phenomenons you can experience in real life, where you can put a you can put an object that is the same density as a fluid, and you can move that object wherever you want in that fluid, and it kind of suspends there in space. It doesn't move around. All right, so let's look at question 4 now. So we go back to our PowerPoint here. If you float a styrofoam block with a volume of 2 liters, then place a brick block on top of the styrofoam block, what mass/volume would the brick need to be to make both blocks act neutrally buoyant? And here's a hint. The buoyant force needs to equal the combined gravity force. So I'm going to show you guys kind of how to set this up, and then I'll let you guys kind of answer because it can be a little bit confusing. So what we're going to do is we're going to go back to our simulator. And remember, we're going to need a styrofoam block with a volume of 2 liters, and then we're going to need a brick block as well. So let's go back to our buoyancy simulator here. I'm going to go ahead and reset everything. I'm going to change from 1 block to 2 blocks. I'm going to make block A be my styrofoam block, and I'm going to change the volume of my styrofoam block to equal 2 liters. And notice, because it is a certain density, the mass is going to change as well, right? And that came from our density mass volume triangle that we talked about before. So you can change one of these parameters and the density has to stay the same because it's a property of styrofoam, and therefore the mass will change as well. So now we have a 2-liter styrofoam block. We're just going to go ahead and throw that in the water. And over here, I'm going to change from wood to brick. And now this brick block, what our job is going to be, let's turn on our gravity, our buoyancy, and our force values here. What our job is going to be is we want to put this brick block on top of this styrofoam block. And we need to find out what the volume of this brick needs to be in order to make both of these blocks act neutrally buoyant in this water. So go ahead and take a little bit of time, find out what this number needs to be, and that will control what this number will equal. And then I will go ahead and answer that question once you guys resume the video. Okay, so we have our styrofoam block in here, right? We see we have a gravity force acting on it. That's our blue number down there, 2.94. We also have our buoyancy force acting on it, the 19.6 when it's fully submerged. Now we have our brick block over here, right? We can drop this guy in. We have 49 newtons acting upward, which is our buoyancy force, and our 98 newtons acting downward, which is our gravity force. Now what we need to do is figure out what kind of volume does this brick need to be so that both of these guys will sit under the water and we can move them wherever we want, and they will act neutrally buoyant. So what we can do is start moving the mass down on this brick, right? Or sorry, excuse me, start moving the volume down on this brick. We're going to just drop this volume down, and we're going to wait until both blocks start floating, right? And what that tells us is that the force of the brick trying to sink in the water and the force of the styrofoam in the water is the force of styrofoam is going to be higher than that of the force of the brick trying to sink, right? So the buoyancy force of the styrofoam is going to be greater than the gravity force caused by the brick. So if we keep going down here, we see that they're starting to float up. Okay, so now that we know that our brick is too small for what we want, right? So we can slowly start to increase. And you see, as we increase, they become fully submerged, and I can pull them down a little bit. And okay, so we see they're still raising. So now what we want to do, now that we're really close, right? What we're looking for is that we want the combined gravity force to be equal to that of the combined buoyancy force. So we see we have this 16.51, 19.6, and then we also have this 33.02 and 2.94. We want the addition between 33.02 and 2.94, the gravity force, to be equal to that of the buoyancy force, the 16.36 and the 19.60. So what we can do is slowly start to increase this. Oh, and we see we went just over again. So I think right around 1.7, let's try 1.71. So now we see that we're at 1.71. I think these brick and styrofoam are moving just slightly down, and we can confirm that by looking at these numbers, right? So if we very quickly, we add 16.76, and we add that to 19.60, we'll get 36.36. Now, if we look at our gravity total, we have a 33.52. We're going to add that to our 2.94. That's going to be 36.46. So we see that our styrofoam block is just slightly, the gravity is just slightly more than the buoyancy force. So maybe if we drop this by one more, 1.7, we see that we get 16.66 and 19.60. If we add that up, that's going to give us 36.26, I believe. Let's double check that on a calculator. 6. Yep, so we get 36.26 on our buoyancy force. And if we add 33.32 and 2.94, we'll see that we'll also get 36.26. And now that is what we were looking for. Our buoyancy force is equal to that of our gravity force. And therefore, if I move both of these objects anywhere in the fluid, they will stay put. So I can move them up. They won't move once I let go. I can move them down. And oops, there we go. They'll kind of stay put once I let them go. Awesome. So that's the answer to number 4. All right, so now let's talk about displacement, right? What is displacement? So displacement is really, goes hand in hand with the Archimedes principle. Displacement talks about the amount of fluid that is pushed away when an object is submerged in it. So we see here that we have a rock and we have this little beaker, and you see that this beaker sits right at about 150 milliliters of water. When we put this rock in the water, we see that there's water that raises up, right? And you can kind of see this at home, right? Say you take a glass of just regular water. If you put anything in there, the liquid level is going to rise a little bit, right? And that's because this object is displacing. It's pushing away that amount of fluid, right? It's now trying to take up the same space as that fluid. And therefore, because the object is more dense, the fluid is going to raise up above the object. So now how can we use this, right? This is where the Archimedes principle comes into play. Archimedes is a really awesome dude. There's a great video in the description box, a link to that video in the description box that talks about the Archimedes principle in depth if you guys want to learn more about that. But for today, let's just talk about this concept right here, right? Which is the buoyant force on an object is equal to the weight of the fluid being displaced. Now, what's really important about this is you can calculate how heavy something is just by submerging it in a tub of water. And we see that with right here, right? So we have a little scale and a little 5 kilogram weight. So see, this scale is reading 5 kilograms and it's out of the water. Also notice this water line is right at the edge of where it can spill over. So if we put even a drop of anything else in here, even a tiny little object, water is going to spill over into this little catch cup. And so once we submerge our weight into here, we see that our object now is only reading at 3 kilograms on our scale, and there's a 2 kilogram buoyancy force pushing up on it. And the way we know that it's 2 kilograms is because the amount of water that was displaced. This water is going to be directly proportional to the buoyancy force acting on this object. So if this water is pushing 2 kilograms up on the object, which is still less than the total weight of the object, so this object would still sink. However, we can find out just how much force that water is acting against that object. Okay, so last thing for today is going to be a fun little video. I'm going to actually cut to me in my garage talking to you guys about how to do this experiment and walking you through different steps if you guys actually do this. Here's a quick little rundown of the different materials you guys can use. I will also talk about that in the video. But yeah, I definitely challenge you guys to do this at home and just see how much weight you can carry inside these little tinfoil boats.
Hey guys, I hope you guys have been enjoying the lesson plan so far. So I want to wrap things up today with our last little activity. This is going to be our fun little tinfoil boat challenge. This is a great challenge for you to challenge your friends, challenge your family members, to see who can build the tinfoil boat that can carry the most amount of weight. So what we're going to be doing is I'll bring you guys in close. I'll talk about the different materials you guys are going to need, different steps we're going to take, and then I'll show you guys how to do the challenge.
So next, let's talk about how we're going to actually build our little tinfoil boat. Now this step, I really encourage you guys to be creative and kind of explore your own designs, but I will show you the basics and kind of the initial constraints we're going to go over about the actual boat dimensions that you get to start with. So first off, I want to kind of show you guys some examples of some boats that we've made in the past and some boats that you guys can maybe take some inspiration from when you're designing your own. This is a pretty traditional little flat rectangle one. It's got a short little wall, and notice these corners here are actually folded over themselves to help seal the water out of the boat when it actually sits in the tub. That's going to be really key for any kind of design that you guys create your own, is to be able to make it so that the folds that you make and the walls you create kind of overlap themselves to kind of help keep that water out while you're testing how much weight it can hold. Here's some other designs we've had in the past. This is more of like an ice cream cone style, and notice again we have that same wall fold over again that you can see on the other boat. This is like an exaggerated version of that corner that is in the rectangle boat. And then finally we kind of have the really quick and easy one, which is like a little cup that someone just kind of rolled into a little ball and then made it as like a little teeny basket. All these designs you guys can try out for yourselves, but I will be showing you only today how to do these rectangle ones. So what you're going to do is you're going to start with your roll of aluminum foil here. So I'm going to unroll a little sheet, and really the way to kind of judge this is you want at least 8 inches here. So if you want, you can come to a ruler here and you can measure it, but this looks pretty close to 8 inches, so we're going to go with this. I'm going to tear off this piece of foil. And here's your piece of aluminum foil. Now, this is where the 6-inch ruler really came in handy, or was really important, because the constraints for all the building in this, for all these boats, is they all start with a 6 by 6 inch square of aluminum foil. So what we're going to do here is I'm going to mark out 6 inches right here, and then from that mark I'm going to lay out and measure 6 inches up here, put a little dot so I can know where to cut to, and then lining up my ruler with that dot and the edge of my aluminum foil, I'm going to put another dot right here on this edge. So now I have actually mapped out a little rectangle here that I can cut out and create my boat on. So I'm going to take my scissors, and be careful during this step not to cut your fingers. We're going to come over here, we're going to cut starting at the first hash mark we made up to this second little dot that we did. We'll turn our piece of foil here. We're going to cut from this mark right here on the edge all the way to that same starting cut point, just like that. Then I'm going to save this little piece off to the side, just in case we want to make another design or you want to give a piece to your family member to make. And now you have your 6 inch by 6 inch piece here. This is a great little starting platform for you to work with, and all boats must be 6 inches by 6 inches piece of aluminum foil. You don't want to have any more or any less, that way everyone has an equal chance to make the best design they can. So now moving forward, how are we going to do these fancy little corners on this boat? So real quick and easy, what we're going to start with, and feel free, you can either measure this out or you can eyeball it. I usually like to eyeball it. I'm going to take about a 1/2 inch to 3/4 of an inch of the edge, and I'm going to fold that over. You guys can see here, I'm just taking that little bit and folding it over. Then I'm going to unfold it. Now we have a nice defined crease right here on the edge. I'm going to do that on all 4 sides. I'm going to work my way around, fold it, unfolding, onto the 3rd side, folding and unfolding, and then last side folding and unfolding. Great, so now we have our 4 sides of our boat. So this next step is really important and kind of hard to see. So you see we have this corner here, right? What this corner is going to do is as these walls fold up, both these walls are going to want to fold up, that corner, you're going to want to put a little diagonal crease right through the middle of it. Just like that. So now when I unfold all this and I lay it flat, it's a little bit hard to see because the aluminum foil is so creased, but you have one crease line here, another crease line right here, and a 3rd crease line that only runs up the center right there. And so I'm going to do that on all of these, make sure they fold outward. A little fold there, these other 2 corners. Perfect. So now it's all unfolded. I have some creases here that are just going to help guide me as I fold this up. And now as I bring these walls up, bring up this first wall, bring up the second wall, I'm going to let this corner piece fold in and down. And so now you see we kind of have that piece that folds in right there. And then I'm going to squish these edges together, and I can fold over that triangle that ended up happening on the inside there. And then you get a nice tight corner, and it's very well sealed off from water getting in. And you're just going to follow that same step all the way around. So we're going to do that for all 4 walls here pretty quick. And the last wall right here. Perfect. And there we go. Now I have my little rectangular boat. And so last little step that I like to do, which kind of helps when it comes to the loading process of all the weight, is you want to make sure the boat isn't entirely flat on the bottom. You want to give it a little bit of a divot right here in the middle, so you kind of roll up the edges. And you can kind of see right there that it's not really flat, it kind of bows out like that. And that helps all the weight kind of sit in the middle, and the boat make sure that all the weight kind of goes right down in the center. It'll help let the boat balance longer in the water. So feel free to either follow along with that design or try your hand at building your own design. Alrighty guys, so last step of this activity is going to be actually test our design. So here's the boat that we just made together. What we're going to be doing is loading this guy up with weight, and seeing how much weight it can actually hold before it sinks below the water. So, fun little part of this experiment is you get to run around your house and look for different items you can use to actually weigh down your boat. You don't have to use weights necessarily. I sometimes like to use coins. These are great because all the same coins have very similar weights, and there's a few different ones to choose from. So you can keep a very consistent kind of measure about how much your boat can carry. There's also different items you can use, is anything that's small but carries a little bit of weight to it. So I have some keys here. I actually went out in the yard and I picked up a few different rocks. And then also, since we're out here in the garage, I grabbed some different nuts and bolts and some screws. So now what you want to do is you're going to need the last supply, which is your container for water. Now this container can be any size, shape, or form. The most important part is that it is deep enough that your boat can completely sink inside of it. That's really crucial because you want it to be able to fill out the most amount of weight until it sinks. The next thing is you want it to actually be big enough to contain your boat inside of it. So notice that this one is large enough that we can put our large square boat in there. This is one of the largest boats, I believe, the design that you can make using the 6x6 inch tinfoil constraint. So anything that's at least, I don't know, about 4 or 5 inches wide, 4 or 5 inches tall, that should do it for you.
Alrighty, so let's test the design we made. So let's take the boat we built together. We're going to go ahead and throw it right here in our tub. I'm going to take that towel that we gathered earlier when we put down all of our supplies and just lay it down right here next to this tub. And now what I'm going to do is choose different weights to put into the boat and see how much weight it can carry. Now this point is really crucial if you're challenging your friends and your family. You want to be sure that you're all using the same exact items. This way it's a fair judgment of who can carry the most. And you also want to go in the same order of how you add weight to your boat. Most designs you want to start with something a little bit heavier. They can carry a little bit more weight than you might think. So I'm going to start with a set of medium keys and just go ahead and throw it right here in the center. And we're going to be real gentle about putting it on because you see the tinfoil can actually move around a lot when you add weight. So this is where it's crucial that you kind of balance where the weight actually goes in your boat. From there we can see that my boat's maybe about a quarter sank. So I'm going to take a little rock and maybe throw it in right here, real gentle. We see that boat's still good, but it's starting to twist a lot. So I might want to add a little bit of weight to the edges. So here I'm going to come in, maybe add, let's go a couple nickels right here on the outsides. Looks like we're going to need a little bit more weight, so I'm going to add 4 more quarters to each edge. And that's starting to balance out the boat. So this is where it's really key on how you add your weight to your boat, is how well it'll carry that weight. If you throw it all in the middle right away, you'll notice the boat will kind of crumple up on itself and then collapse. So it's really key that you kind of add it slowly and methodically all the way around the boat. So you're going to want to keep doing this until you notice the boat is starting to get real close to the water's line edge. You can see right here, we're just about to pass the edge right here. So I might add a little bit more weight over here. Grab a few more coins, kind of load these guys up. We're getting real close right here. I think with just a few more coins, we're going to end up going over.
More pennies. And we see just as I run out of coins here, I think this water is going to breach the edge. Oh, and there it goes. All right, so now we have a measurement of how much weight this boat can carry. And so now when you challenge your friends and family, you want to start with the same heavy items and then slowly start to add those lighter items like coins.
All right, you guys, thank you so much for joining me today. I hope you guys had a really good time. I hope you guys have a lot of fun doing this experiment with your friends and your family and challenging each other to see who can make the best design, the best boat. Please, if you have any more questions, feel free to comment down below. Or if you want to find out more or just see different resources, we have all those down below in the description box for you guys to click on. Also, be sure to check out our other videos that we're going to be putting out, and stay safe during this time. Have a good one, guys.
Hey guys, so last topic for today is going to be talking about careers in engineering and physics, right? So why would you want to go into engineering and physics, or what are careers that you can explore in engineering and physics? Let's talk about a little bit about the engineering side, right? So engineering, we see with these red bubbles, these are kind of the main concepts and sort of attractions you're going to have for the engineering field, right? It's really going to be focused on design, building, right? Machines, structures, systems, these different kind of tangible working integrated objects. You really be looking at thinking about how does, say like, how does a lever help you push another object, right? How do you open and close a box? How do you get a car to move, right? What are the different systems inside that car that help make the car move? How do you get the car to slow down? How does that system integrate with the car itself, right? So talking about like brakes and such like that, as an example. And then if you look over on the physics side, physics really focuses on nature, force, matter, energy, right? Properties of how things are, right? Why does a thing do what it does, right? When I throw a ball in the air, why does it come back to Earth? When we shoot a rocket into space, why does it all of a sudden float when it gets far enough away from our Earth, right? Really talking about the how and the why our world works, right? How do we explain the way our world works? Where engineering focuses more on how do we take advantage of our understanding of how the world works. And so these two are very closely related, right? They always help each other. Engineering designs different systems, and we experience phenomenons that physics can actually observe and then use their understanding of other concepts to help explain. And so we do this through math, human interaction, and innovation, right? Always pushing concepts, right? Engineering, you can stumble across an idea or notice something happening and you can explore that idea. And then physics can come down and observe you do that and then help better explain as to why that is happening in the way that it does. And this happens through human interaction, right? So you're always going to be talking to people. You're always going to be sharing what you're learning, helping people, or teaching what you learn to other people as well. And the way you teach this to each other is going to be through math. Math is the universal language of engineering and physics, the universal language of the world, really. You can have anybody who speaks any language can look at the same math equation that you are and understand how and why it works, right? They can work through it. It really is a language that helps us explain our world, right? It explains these concepts in physics. It explains the concepts in engineering. It seamlessly bridges the gap between them and lets them work with each other. So finally, I want to thank you. Thank you guys so much for sticking with us through this workshop. We hope you guys are being super safe at home. We hope you guys are making the best of the situation. Definitely I hope you guys have fun working on that tinfoil boat experiment, and show your friends the tinfoil boat experiment, show your friends this YouTube video so they can learn more about this as well. And you guys can have some fun playing with the Phet buoyancy simulator. And finally, I want to leave you guys with one of my favorite quotes, which is from Albert Einstein. And he says, "Scientists investigate that which already is, engineers create that which has never been." This is something that I find true and dear to my heart because as a STEM major, as a mechanical engineer, I love to build things. I love to create things, design things, and see them happen in the physical world, right? Bring an idea that was in my head and actually create it in the physical world. That's a really cool concept to me. So scientists help us understand what is around us and how we can use that. Then engineers can use that information to help actually create what has never been before, right? How do we make a plane, right? How was a car first made? And we use that from the information that scientists gave us. All right, so thank you guys again. I hope you guys have a great day. And come join us for other videos that we have posted up on our YouTube channel. Thank you guys.